Good morning, everyone. Today we are going to discuss about this memory networks. So we are going to be three presenters over there: Rajan, Joel, and Sravani. And just a brief overview of what memory networks are. Uh, from the time that we have started off this course, we have came up with multiple number of approaches to deal with the real-time problems. So one of the problems that are there presently, and that's still not very much in the hands of the users, is the fact that we have a very limited memory when it comes uh, to deal with the real-time objects. Okay, so when we are saying this thing, object reorganization doesn't require the memory level. It requires a very low level of memories. But for us to really come with the real-time solutions, we need to have a systems which can gives you the memory as well as embedded in it. So our attempt is to add a long-term memory component in order to make it more like artificial intelligence. Means we actually compare these neural networks with the brain all the time, but the fact of the matter is that the long-term memory component has to be there in order for this particular type of networks in order to become complete with artificial intelligence. So when it comes to the memory networks, we have two types of memory networks: strongly supervised memory networks and weakly supervised memory networks. We are going to get to the brief of these two types in some time. Okay. So, one of the things that comes when we go for this memory network is the question answer model. So normally the whole education system revolves around this particular things about the questions and the answers. You just put some questions and the system replies you with the answers, and the answers use those logics or use those embeddings that we used to learn them earlier. So in this problems, that it really boils down to the very concept of the question answer problem, the memory networks. So questions. The problem with the questions is the questions sometimes are very much easier. Like it could be in a single line, or these can be inference type questions, so that it has to refer back to the grammatical meanings and do all this stuff in order to get okay what's the inference of these things. So whenever we are going to really do this memory networks, we are going to actually label those with answer label or supporting fact label, because actually we're going to have to learn the system. Okay, this is a supporting fact. These two things going to add up in order to give the answer out of it. So we are actually going to see how these memory networks are going to behave. So there is one example. So we have a three lines. Okay, the Sam moved to the garden. Sam went to the kitchen. Sam dropped apple there, here, there. Actually, it should be there. So firstly, the question is, where is Sam? So if we have to make the machine learn about this, so we have to really see, okay, it's in the single line. Sam went to the kitchen, so Sam is in the kitchen. Okay, but when the complexity we increase it to one level more, where apple was dropped, so now apple has to become from this particular thing. Now it is with the Sam, and Sam is in the kitchen. So fundamentally, it requires you to move from one hop. One hop is basically the one single embedding which you have to the other embedding. So it's all about getting those embeddings embed in the vector space and to get the extract out of it. Now, now this particular data set, Joel is going to go dig into in much detail, but this was a data set that was released, and you can see the complexity of the task that's was given. There is one single supporting fact where is Mary is simply answered by in a single line, whereas two supporting facts, like same as in the case of a Sam, where is the football? So we have to really see, okay, where who possesses the football, and then who the person who possesses the football is in which location. So this is particular the human intuition that comes into play, and we'll have to see how machines are going to really react in the same particular manner. So the path finding is also like a complex manner. How do you go from den to the kitchen? So it actually involves two or more things, like west and the north. So these two hops are going to come into play, and this thing, how do you go from office to the bathroom? This also has to come with one or two hops, and the same is the case with this particular thing, where the questions come with the motivation. So as in this sort of a question answer, it basically comes from the very fact that we have to look out to the various questions and to come with the answers. So the good way to start with it is to start with the single supporting facts, so that we actually know how to really deal with the single supporting fact in a very good way, and then to learn the machine progressively in order to go for agent motivations or a pathfinding sort of examples to really put in the frame. Okay, and one of the things is that even if it's actually difficult for human beings to also to really come up with some of the inferences when it comes to it's actually the thing being is it actually uses the many diagrams of the grammars, and one thing is related to another in a particular fashion. So you have to involve the very logic of the how the author is written. So we have to see how machines could really progress in that way so that it can get to that particular thing. And one of the problems with this thing that we are right now implementing it in on a single language, that's English. But when it's come to the regional languages, the overall complexity is going to increase, and that's going to be the broader framework in order to us to persuade such sort of a memory networks. So right now we are actually seeing the components of the memory network. So there are going to be the 4 parameters: input, generalization, outputs, and the response. Okay, so input, what we do in the input is that we convert input data into the feature map. Secondly, when we actually converted the input map, we actually have to update the memories with the new inputs, and that process is called generalization. Output gives the producer new output based on the question, and the response actually converts the output into a response that can be seen into an output world. Means ultimately the system will come out with the one single word, but actually when you're going to give it in to the output of the user, you actually want it to be in the form of a sentence. So how do you want to actually grammatically put those sentences to have a better correct sentence and to come up with those things is actually basically going to be done with the RNN. RNN would be used for these things. So for the input, we are not going to do any conversion. We are going to keep the original text. And then in the generalization process, we are going to really store this embedding into the next memory slot. And then for the output, we really have to have the iterative process in order to loop multiple number of times in order to get the right answer. So this is like our generic architecture where we're going to have this input module where all the systems are inputs are going to fed, means all the hops are going to fed, and then it's going to be in the form of embeddings, and then it's going to store in the form in the memory, and then based on the question, the whole output is going to come from there. So this is like the same example that we have took. Okay, so this is actually showing how the memory module is working. So we have these 3 inputs. Sam moved to the garden, Sam went to the kitchen, Sam dropped apple there. So these all are going to really save as the memory, save in the memory embeddings. And when the operations are going to perform like a dot product plus the softmax, we are going to have the weighted sum. And from the weighted sums, we are actually going to compute the questions in the answers of the question that is being asked from us. So this particular diagram gives you a memory description of that whole implementation.
Do you guys have any questions so far? Because I think we're going quite fast. No problems? Everyone on the same page?
Okay. This one, why is it that softmax?
So where does the coefficients come from to get the weighted sum? Is it based on the question? So you have a secondary arrow coming from the question where it's Sam, right? U1.
Yeah.
Right. So the vector, which is the embedding of the question embedding is sent into to the memory module to do the dot product and softmax, and then out comes a weighted sum for that. So what's the second arrow U2 going to? So this is, you take all of the factual inputs, 1, 2, and 3, right? M1, 2, and 3, you do their weighted sum, and out comes U2.
Yeah.
And what does U2 represent?
U2 is the output to the question, the answer.
The answer of the question.
So in a sense, the weighting serves as to provide something like soft attention for the entire question. So you weight different, you weight certain answers based on your previous set of memories. So you give a focus to different areas of the memory. Yeah. So each memory, or rather each sentence, is is compared to your query, and you sum up what is sum up again? You sum up the embedding of the input sentence, the dot product of the embedding of the input sentence with
So let me just get clear about the coefficients. These are coefficients over the entire utterance M1, M2, and M3, right? Not attention within it. So this is just just some weighting of those embeddings themselves, right?
Yeah.
So you compose the input representation after this weighted sum. So the weighted sum is the input representation.
I believe so.
And then there is another part, the controller, that's taking the weighted input vectors and then trying to calculate the output, right?
Yes.
So U2 is not the output, right?
U2 should be the embedding of
The embedded version of the output. So what's doing the computation between here and here? There's something in between, right? Because this is just a representation of the input, is it? Weighted.
Yeah.
But something has to use that to then compose and then come up with the answer, right?
Yeah. I think when I read the paper, there's a there's a
GRU component.
Yeah, GRU component in the middle, but I can't remember exactly how it's used. Yeah.
Okay. But the inference mechanism isn't shown here, right? This is just the weighted input representation, and then somehow from there you're getting to U2, which is the embedded version of the output, right? So you're saying that the kitchen is actually represented by U2.
Yeah.
Or is it like, in this example, you're using these three numbers, 0.1, 0.7, 0.2. Are you saying that because your M2, the second component is corresponding to kitchen? So are you saying that here you're using like 0.7 is larger than all the rest because your answer is kitchen?
0.7 is due to the question that where it's sent.
Yeah, where it's sent. But then you see like the final answer is 0.1 times M1 plus 0.7 times M2. And then M2 in the storage should be corresponding to kitchen.
Yeah.
Doesn't M2 correspond to the embedding of the sentence send when to kitchen?
Maybe. Maybe M1 maybe the 0.1 could be the product of each hop. So like when you do a hop, you look through the set of all your memories, and then you find the one with the highest relevance to your current query, and that would but it doesn't give you a number at the end.
Well, it's clear that this is specifically the weighting for the specific question, right? I mean, if you believe the coefficients, you see 70% speaking of this sentence, right? And the rest of the other two sentences, 1 and 3, receive relatively low coefficients, right? So it depends specifically on the question that you're going to engineer this attentional, I don't know whether you want to call it attention or not, but weighted linear sum of the embeddings. Right? Do you guys have a paper reference? Is it in the slide yet?
There's I think it's the one by Facebook AI, the memory networks by Jason
From Weston.
Yeah.
Yeah, I mean, if anyone can find the paper, go throw it up on Slack. So we can go. I was looking at a different one from Learning End-to-End Goal-Oriented Dialogue. It's the same one as what you're talking about.
I think for this particular diagram, it comes from a separate paper. I'll post the link.
Okay. Thank you.
Sorry. It's really there. Okay.
Well, I posted one of them. I don't know whether it's the right one. Okay. Welcome to go ahead. So Eugene posted the paper, right?
So actually, when we are actually doing the dot product and the softmax, what we are doing is we are actually doing the scoring function. So when question answers are being mapped using the word embeddings, the word embeddings use these different words, whatever these are, and actually put them in a low dimensional vector space with the advantage to calculate the distance between the vectors. So the weighted sum that are coming are actually calculated after when we are actually have put those words into a low dimensional vector space. So as a like question, where is football? So actually the question actually will come down to that the hop in which that football is mentioned. So it actually gonna put those in the vector space and going to see which is actually quite a bit nearby to the football, and John is going to actually be the actually person who picked the football rather than the answer which is actually where the football is. So actually, so the answer is that so how the scoring function is going to implement is it's actually implemented with this particular embeddings in the memory networks, where Q is the question, D is the answer, and U is the matrix by which the words embeddings are obtained. So actually, so this is actually a way of representation of the scoring functions that they have actually extracted the scoring function out of it. So someone has any idea about how they, because this is actually basically going to be the key essential part of our scoring function, and so we're actually going to do we are going to take the question and we're going to take the answer, and we're going to have a matrix in which the words embeddings are obtained. So actually basically doing this particular thing over there. It's actually having the question, it's having the hops, and we're actually going to get something out of it. So this is basically representing the scoring function. So now right now we're actually moving to the how the really architecture implementation of the memory networks is, and so actually so as we can see, okay, so we have these sentences. So these sentences act as the input, and when there are two embeddings that are going to be out of it. That's going to be embedding A and embedding C. So whatever your question is, the question will formulate the embedding B, and it's going to be alongside with all the sentences that are coming from embedding A, and there is going to be the inner product between the questions and the answers. So this particular thing, after the softmax and the weighing average, it's going to give you the weighted sum of each and every particular embedding of the sentences when it actually did the inner product with the question. And then after that, we're going to have this whole weighted sum that actually came out of it. And then we're going to actually take it with the question, and the whole softmax layer is going to actually come in the picture in that. So there is actually two softmax implementation. One is out there and one is actually out there. And this is actually how a single layer network is actually implemented. You want to have a word on that?
Sorry.
Do you want to have a word on that?
About what? As in
The whole architecture.
the whole architecture. Okay. The memory network is what to talk about. So
Where's this diagram from?
this diagram is from, I think, end-to-end, the end-to-end neural network paper. End-to-end memory network paper, sorry. What's the name?
Is there any difference between embedding A and embedding C?
Embedding A, embedding so the embedding. So for embedding A, right, it's passed into. Wait, how should I say this?
should like embedding A represent what type of question I can answer, and embedding C should focus on what's the actual answer to the question? So embedding A would represent something like I am in place. So if you ask me about where I'm important, and embedding C would be kitchen. And so isn't the first dot product deciding which part is important, and the second is actually using the important thing to decide the answer?
So actually, all three of the embeddings are different. There's embedding A, B, and C, and they're all trained. So if you look at the paper that was just posted, if you look at the diagram on page 2, there's a paragraph right before it, and it states what I just posted in Slack, right? So it's basically retraining embeddings of the words, from what I understand, to try to minimize the cross entropy, right? Minimize loss on being able to answer questions, right? So the embeddings are different, but they are being used to represent the same sentences or the same questions, but they're attending attending to different functions, right? So for example, embedding A is saying, how best would I represent the sentences as related to the questions before waiting, right? And embedding C is like, after I know the waiting, then how best would I represent the information so that I can achieve the vector O, which is the output representation embedding for that one all of the contextual information I would need to know the answer, right?
And so why do I have only one embedding for the question? Wouldn't the same logic imply that you also want to have like an embedding D for the question?
Embedding for the question.
Like
there is an embedding for the question.
Embedding B for the question, right?
Yeah.
But you and then you have two embeddings for the sentences.
Right.
Couldn't you also argue that instead of using embedding E twice, you have because you use embedding E again for the sum?
Yes. Mm-hmm. Yeah, you can see here both of the inputs are the same, right? There's a U and a U, all basically taking question Q and then embedding it, right? So the input representation of the sentence, sorry, the question is the same. Before it gets, before it's helping to transform the context of the narrative, right, which is resulting in O, and also when it's being fed into the final prediction. So your question was?
Couldn't it be also beneficial, like to use different embedding for the second part?
So you're saying instead of doing this through B here, you could keep this, but say you train another embedding to go in here.
Yeah.
What do you guys think about that?
The lesser embeddings, the better.
Right, so it could be the case that we don't want to do that because we want to make sure we have fewer parameters, and so training another embedding could be costly. But again, training an embedding is separate from training the model, right? Because the embeddings are a separate set of parameters you need to estimate.
So this is actually a single layer network. When it comes to like, so we have a multiple layer also in which the same output of the given sentences are actually going to hop around. Say it's going to be the same, and the same input is actually going to be passed to a similar level of information, the input layer and the same output layer. So it's actually the same network, but this part is actually being repeated once after another, and there is a summation over there. Actually, this actually is a multiple layer implementation. Version of model. Yeah. So, so wait time. So actually, when we are seeing in this case is that when this question is actually being is actually having the inner product of with this embeddings, we can actually see the products are having a variation in the colors. So actually, these are representing a 0.7 or a 0.1 in that case. So actually, somehow the product is actually going to come over there from the weights. So the same thing of weight time is going to come over there. That how we are actually indicates how weight vectors are multiplied to input and output components. And there are actually two schemes out there, adjacent and the layer wise. Uh, and in the adjacent, we have these similar to stack layers, output embeddings of one layer are the input to the another layer, and the layer wise implementation it remains the input embeddings remain the same for each layer. So actually this sort of implementation, but two different sort of inputs, how inputs are going to be traveling on that things for the wait time. Yeah. So this model selection. So model selection really comes into the picture. So we actually have a two possible approach for the model selection. So firstly, for whatever sentences that we have, we actually pick the words from the same and we actually embed them in the words, and we actually come out with some resulting vectors that doesn't take the context of every word. So basically it takes the every noun or verb in the sentence and actually put them into a vector space and then doesn't take the context of every word. Where in the positional encoding, we actually take care of where the context is, where the words are, and when you actually put it into a low dimensional space, we actually take care of that. So these are basically actually going to be the model selections. How we are actually going to proceed for that.
All is that. So maybe I didn't focus at this point.
You guys must have questions. Come on.
I think it's
like the context is more.
yeah, but we actually start with the simpler things before then actually going for a positional encoding. So it's actually better to have a batch of words in the place, and then because actually in the case of a language, the only thing that matters is the context. Okay, so you can have a similar word but with a different interpretation depending on the context. So this is actually the same level of approach. So maybe they have started with the bag of word model first, and then they have shifted to a positional encoding in order to get the right results and accuracy is actually measuring at some point. So Joel will continue.
So they also, in that same paper that we are looking at, which is the end-to-end memory networks paper, they propose a couple other models. Right? So if you read, I think section 4.1, they go over the first two things that are on the slide, right? The bag of words model in the paragraph saying sentence representation, and the positional encoded one in the second paragraph after that. But they also say, following that, they have a paragraph on temporal encoding. Right? So for questions where you actually have to know a certain state of the dialogue and then move from there, they have also presented another one.
Yeah, actually, when you actually see on the first example that we took now, actually, in this case, we have a temporal example. Like, so Sam moved to a garden, and then afterwards, Sam went to a kitchen. So there is a temporal component also to it. So we have to actually see where that whole temporal thing is coming to. So our third model organically is going to be this temporal model in which the time thing will come into place. So these are like different sort of implementations one after another, which can be done in order to make the memory networks more implementable or more better with higher accuracy.
if you need to have permission.
All right. Oh, wait to come. Oh, yeah. That's now just not going to come.
Can we switch the laptop? The presentation is.
That one? Sure.
No, I was just saying that you need to run control from.
Yeah. You want to present from which laptop?
You just use this laptop.
This laptop. Okay. Sure.
Yeah. Everybody should be able to. Yes. Yeah, so this is basically the notebook from the Fast.AI course. Yeah, so over here they use the Barbie data set, which was, as mentioned just now, the data set used for previous two papers as well. So so I think the bulk of the main portion of the network is below. So the part above is just the passing, and the main contents of the network is important. Nice. Yeah. Yeah, cool. This is diagram as well. I'm gonna actually open up the diagram. If you refer to the diagram, yeah. we have this right here. So we have a question embedding which goes into a memory module, and out of the sentences in the stories that we have, one embedding is passed into the input network, and passed in input, and the other is passed into the output, which are then combined in the end together with the questions embedding. So you see how this is implemented over here. We have a here we have a merge layer which takes the embeddings of the story, which kind of functions as a memory, appended to the embeddings of the question, and the dot product of both embeddings are taken and subsequently reshaped and applied to a softmax layer. So this corresponds to, I believe, this particular portion of the network. Yeah. So for the rest of the lecture, Jeremy goes on to talk about attention models, which is a build up for, as well as soft and hard attention, which is a build up for the subsequent lecture. Not really shown here, but yeah. Does anyone have any questions at this point?
Are you guys clear about what type of answers this type of memory network can produce? Can it produce a phrase answer?
It should be able to.
If I read the third bullet in there, right, it says, finally we pass the weighted average through a dense layer and classify with respect to a softmax into one of the words in the vocabulary. Right, so what does that tell you? Can it produce a phrase output given the certain architecture? No, right? It's basically trying to classify against all of the words in the story, which word is the most likely answer to it. Right? So it's basically doing a classification against all the words in the story.
We found a very specific type of question, and so like we heavily relies on the fact that all the sentences follow the fixed grammar. Yes.
Similar grammar. I don't think it's
almost, yeah.
Yeah.
So I mean, in this setting, to create an answer out of the words that you relatively use, because that's again follow the grammar.
You have to use RNN in order to give the sentences out. So that's going to be another layer over it. Especially it has to come with the right words. Then you can get good sentences out.
That's interesting. You can just replace the question word with the answer word.
Yeah, I don't think it's, the representation is trained over the, it's still somewhat language specific, right? Because the story and the settings are trained for that. So let's ask another question. Why would having multiple layers in a memory network help? Or maybe we can ask an easier factual question. What is a hop? When they talk about hops, one hop or three hop network, I think that's quite related to the same question.
I'm saying that a hop is a common sense one hop means that the answer is in one sentence. Two hops means I have to combine two sentences. Basically, first I have to figure out person and another sentence which can give a question. And to get to your first question, with multiple layers, you can do exactly that. Like you figure out basically the first step of the answer, and then the second step. And the more layers you have, the more steps interconnected sentence.
Is that correct? From what you
Yeah,
guys understand?
more or less. So you look for the first sentence, and then then you take the dot product of that and your existing your query, and then you look for the next sentence, and depending on the number of hops, you will take that number of sentences. Then they also say that in general, about three hops gives optimal performance.
For the data set that they do.
Yeah.
That always needs to be qualified, right? So if you were to put a softmax over the output at every layer, what would you get? I mean, right now you're just doing the softmax at the final layer because you want the answer. So if you put a softmax at all the intermediate outputs where they have fed the question through and already done the dot product of the story, would you get something like what you were saying? So you would first get from the first layer, okay, the person is being intended to, and I know that the softmax is saying, I want to pay attention to the person whose location we want to know, and then for the second softmax, you get the location. Yeah, the keywords of each piece of logic needed to come up with the answer. So, for example, let's say you had a very complicated story with many people and many locations. Okay, and you ask different questions about the locations of different people. Could you just take the output of the first layer, first network, remove it, and then artificially say, I want to know the location of the second particular person? So instead of using the output of the network to determine the person is important at the first layer, just artificially insert it as the embedding for that person, and then run it through the second embedding layer, the second level, and then just find location. Would that be possible?
Because the location also is dependent on the context. So I don't know if just looking at the question for the person that you want to start, you know, that involves.
And they ask the question to do, and what it actually ends up doing, and the partner in the same thing.
Sure. No comments. There should be lots of interesting discussions for
I wonder, like, if you have a complicated, like, multi-layer network and you ask it a very simple question, and it's still answered, or is it like basically getting totally lost because it requires lots of interference and hopping? Like, you ask it a one hop question and you decided to answer three hop questions. Do you have any chance of actually getting any questions?
So anyone want to possibly an answer to that? You have a multi-layer memory network that's only given simple questions that you could answer for one hop network, but it's still able to answer it.
One of those layers could answer certain levels to then pass it on to the
Yeah, I think we'll definitely be able to learn it. You're just over parameterizing. So it may be that you end up having some problems with overfitting, right? Because basically what you're asking the network to learn is one layer needs to come up with the answer. And the rest of the layers are just doing something like an identity, right? But because you're not constraining the answer to be in any one layer, actually each individual layer could be computing some nonsense, which together comes up with the answer. Right? You're not saying that the answer must come out from the first one. So it's quite possible that something else. Right? But I think yeah, the problem always is like you have too little data to manufacture good parameters for the code. Okay, cool. I'm surprised you guys don't have much to say. Did you guys watch the video? No.
Talking. Not sure if that that's the link. Trash talking this application, but like I was surprised because he kind of said it's over advertised in a meaning that like it was like the paper was advertised as coming up with intelligent chatbots. And when you like looked into it, the structure is relatively simple and like the type of questions it can answer really well. So he said that probably he doesn't think that memory networks is the area for this type of application. But there might be other applications for them. Have you guys any ideas about like, other applications for memory? Even this type of architecture could be useful.
I think there's a lot of applications for this. This is sort of like work that's not quite ready for mainstream, but it's demonstrating a promising application with a very simple architecture. So for example, if you wanted to do question answering in video, which is something we're not quite there yet. I mean, imagine like you're walking around and you're completely instrumented. You don't remember where you placed your homework assignment. You can ask your memory network, where did I put my homework assignment? Right? And it would be able to retrieve it. It would say, you know, go back to whatever room and grab your homework assignment from there because that's where you left it. No, it's because I can imagine that you could do this in a multimodal setting, and then the multimodal setting you would have information that's useful at various time steps. But I think in general, you're going to see research more like this in the future, not in the sense of this particular topic. I mean that you're going to see papers that have like suddenly an exploding gradient of citations, right? So it just came out last month and it already has 25 citations, right? Or something like that. Because, well, because of archive and because of other work, models are getting glamorized very quickly. And this is something that I will talk about in a keynote talk at another conference later. But basically, the problem with archive is, and we've discussed it to an extent, is that it basically gives a lot of weight to very, very few individuals in research. Okay, even though it seems like it's a democratizing procedure because every paper can be publicized. I mean, you know where the papers are coming from, right? If it's from Bayer, for example, okay, I gotta read it. Right? Or if it's coming from Stanford, I gotta read it. If it comes from NUS, I don't need to read it. Okay, but especially if you're a low-ranked institution, that could be a problem. But more importantly than that, I think is because things get glamorized so quickly, a lot of longer-term research gets marginalized. Right? Everyone is thinking about, okay, the paper just came out yesterday. I better be experimenting with it now. You know, wind back to maybe, even 5 years ago, at least you had a couple months of time before you had to worry about it. In a lot of conferences, like I have to deal with SIG-IR rejections and submissions this morning. People are already saying, you didn't compare to last week's paper, and the review process is 3 months long, so it's a little bit absurd, right? That things are like that. So we end up in the research community with a lot of papers that are incremental because they are all just based one stacked on top of each other. And then foundational research gets marginalized because you don't have the capability to think hard and long about problems that are not well formed yet. So you'll see more problems with this. Yeah, so I think I would say Jeremy's not quite right to trash talk about it. I mean, when deep learning first came out, there was a lot of trash talk about it, right? I don't know whether you realize people were saying, how can all this simple math be any good, right? But it's because of the exponential increase in data and computational firepower that we're able to do things this way. Although it's clearly not a very good use of computation, there are certainly better models for it. It's just that nobody's really gone and figured it out. It's sort of silly that something like a ReLU makes a lot of sense. There's not much underpinning it. Just, I want to pay attention to certain regions, and that's the way I do. So what I mean to say from all this is, I think there's a lot of collateral damage to deep learning in the fact that people aren't not really thinking hard and fast about a lot of the problems. Because you can make advances with very simple things, and you can still layer a lot of complexity on top and still get good performance without understanding what's going on, your foundational aspects are being lost. So it's up for all of you in the room here as PhD students and undergraduates who are coming out of the universities to go back and say, okay, all this deep learning stuff is great, but let's go figure out why it works. And there's a lot more model improvement to do. I mean, you look at the models that you see there, they're so simple. I mean, there's a lot more that can be done in optimization and explanatory. Okay, go ahead. Was there more in your slides you wanted to talk
I think there's one other presenter.
Okay.
Oh, okay. Then I don't think we have more. Yeah.
Okay. Don't have anything else, but there are more slides in your deck. Do you guys want to go over it? No.
It's fine.
Okay. All right, well, we have another 10 minutes or so. What do you guys want to do?
Oh, okay. Actually, we could go to the.
If you're not sure, we can just do it together for the last 10 minutes. I mean, again, this is supposed to be more of a discussion group. It doesn't mean that the lecturers have to know and say everything. Because all this stuff is pretty new too. I mean, it's only been about, what, a couple months since all this stuff comes. You guys want to find this paper, Memory Networks for Split Memory Architecture? I don't even know which one it is.
Use the video here.
I think those set of slides are based on this paper that I couldn't see.
Yeah, I think that one.
So you look at this paper in the architecture diagram, basically what they're doing is something like taking the question answering system and then proposing something that is taking a user persona into consideration.
Yeah.
Right? So you go back to the slides that's present there, right? They're basically manufacturing some type of user profile on the right-hand side there that's based on the user and using that to attend come up with an answer specifically for that.
Okay, so what they are doing is actually basically based on your profile, whether you are actually a elder or a younger person, they're actually greeting you in a different words. If you are an elder person, they will greet you with okay, greetings, sir. There is one other example in which actually they will go in a much more friendly word and use the word to assist you, and they change the whole grammar based on how they want to really but switch on your profile. So this is like one of the things that they are doing. So they are constantly weighting those hops based on your profile and giving you the results in that form.
Mm-hmm.
So there was yeah. So they are actually basically kind of personalizing the whole experience with the user of the chatbot. This is one of the examples where chatbots could actually.
Was this in Jeremy's lecture too?
I don't think so. This was from another talk we attended. I attended the TensorFlow meetup. Yeah.
Oh. Do you want to go through any of the examples about what happened to them? So this one seems like saying that the standard memory network doesn't do the right thing here, right? Basically skips to something where it says I'll start the request now, although it's not clear what should be the case. Is that right? Correct answer predicted answer. Or is this a good case? This example is not from the paper. Or is it from somewhere else?
Oh no, this example is what is that? Okay. No, this one from a separate set of slides. Yeah. So I believe what this particular diagram here is talking about is
What about the following one?
oh, this one. So yeah, I think these three sets of slides illustrate the flaws in a typical memory network in the sense that it's not able to personalize the response based on previous dialogues. So if you look at this particular slide over here, it says the user has actually indicated uh, wait, what one is Yeah, about what the user previously did, but wait, no, that doesn't make sense.
It seems to be forgetting that it's the user taking the time. Because it answers asking again what are you looking
Ah, yes, right.
The predicted answer is what food are you looking for, right?
Yeah.
And the correct answer is to ask about the economy solid one.
So I guess the solution to that was is split memory architecture. So where's the architecture? Okay.
So maybe you guys later can just help narrate these last couple of slides in Slack,
Sure.
because it's a little hard to figure out what's going on in these.
Yeah.
Yeah. Whether it's supposed to be a shortcoming of the original network or something. I mean, you have some notation on the side, but it's not like, or at least tell us where the example comes from.
Okay.
Okay, so that's it for today. So next week we have our final one, our final lecture. Unless somebody wants to do the last two lectures, which is the neural translation and time series experimentation, we're not going to have that. Okay, so right now we have attentional models. Next week, presented by Edwin, and you as well. Right.
for. On interest and Edwin actually. You may need 2 weeks to put it together, or is it like one topic?
Well, we have two other topics that we haven't covered in the Jeremy's class, which is the neural translation, which is slated for week 13, but right now, the class ends after week 12. And reading week, there's another one for time series and experimentation. So if you guys are keen to have that, we can just meet anyways, and then we can have somebody try to present from that. What do you guys want? Do you guys want to continue, or are you happy ending it early? You want it? And Gabrielle says yes. What about the rest of you? Have a show of hands who wants to continue? And who wants to finish off? Okay. So it looks like we'll continue. So week 14 and week reading week, I'll ask you guys to sign up for one of them. So we'll just have the whole class sign up for one of those two sessions. Okay, and then it won't be on anyone's responsibility single-handedly or with two people to present. Again, this is really a discussion group. The fact that we have presenters just means that somebody has bothered to watch the sessions for sure, and has bothered to come up with some slides for sure. Okay, but it doesn't have to be that way. It can just be a discussion group, which is what sometimes it devolves into anyways. Okay, so next week we have attention models, and the week after that we have steps. So hopefully you guys are getting ready for that. Okay. All right. Thank you very much. See you next week.
Yeah, I think I'm gonna make the.
After yourself.
Yeah, so I'll make the same offer as I did last semester. If you need to print your poster and for some reason you're not in SOC, please send your posters to me by hang on.
Monday or Tuesday. Before.
Monday or Tuesday, yeah. Wait, no, by 13th of April, because on Monday and Tuesday I'll need school. Yeah. So I'll print it for you then. Just let me know when you want to collect it. Yeah.
So next week, Friday, is the deadline for Joel to help you print out locally. And then, Joel, you can put the posters in the undergraduate office.
Okay.
And we'll keep them there for you. Okay? I'll put up the slide template if you want to use it. Again, I apologize, it's pretty ugly. You're welcome to do a better job of the design. But if you'd like to use that, you can use it for your template. Okay? Thank you, everyone. See you next week.
So, how far is it? That we can go into one as we